what if I go like this? This is a fluorine. Okay. Now which one's more acidic?
The top one.
Because it's
Closer.
closer, so it has a stronger pull. Here, you can think of it as closer, so it's pulling them stronger, or you can think of there's even more electrons around here, so there's more electrons of fluorines pulling on, so it has less of a pull on that one. Cool. So you can just know those trends. I think you'll see that on the test, like which of these is more acidic, and there'll be some that are closer, some longer, some more, and so you'll just be able to compare there. And just knowing that, okay, I like to do this before I go into the next example, or the next, which of these are more acidic?
Is the chlorine? The top one.
Top one. Think of your periodic table. Fluorine is above chlorine. Light, right? Our electronegativity trends. Fine, beautiful. Our fluorine's here, our chlorine's here. Electronegativity increases as you go across and as you go up. So fluorine is more electronegative. So this one is more acidic, right? Okay. Now let's talk bond length. And this I think tripped me up a little bit when I first learned about it. Which of these are more acidic?
Chlorine.
Chlorine is, right? This might be a little counterintuitive because here we just said this one's more acidic because fluorine has a stronger electronegativity. Here though, the hydrogen is directly bonded to the halogen. And this is probably the only time you're going to see where bond length plays a role. And so why is this chlorine more acidic?
Because it's in the 3p orbital, so it's further energy.
Yeah, we think
to the hydrogen.
And even just going bond size, this fluorine, pretty small, right? So it's bonded really close to this hydrogen. This chlorine is considerably bigger than that. So I think of it like Pluto versus, like Venus and Mercury. The sun is like the nucleus of the halogen. If Mercury has it's held stronger to the sun than Pluto is, because Pluto's so far away that, something could just pull Pluto away if it wanted to. I mean, we've kicked Pluto out of being a planet, sadly enough. Here, if a base comes along, and base is negative, and says, hey, I want a hydrogen, this guy is going to be a lot easier, because the chlorine's not going to really notice this hydrogen leaving. It's not going to really care. This hydrogen, because it's smaller and the fluorine's small, is going to be holding onto that hydrogen really tightly. Does that make sense? And here you're just you're comparing things that are hydrogens bonded directly. Here, it's not bonded directly to the chlorine or fluorine, so we're just really comparing the electronegativity of them.
Because when they teach it that way, it's almost like they're not strong acids, but they're both strong acids.
They're both strong, that's all you're comparing it to, but when you think of HF is 3.1, but HI is negative 10, so HI is a lot more acidic, but hydrofluoric acid is still really acidic. Now, the third thing that affects acidity is stability of the conjugate base. I think this is the trickiest to understand. I guess first off, what are your guys' understanding of stability of a conjugate base?
The more resonant structures that the conjugate base can hold, the more acidic the acid is.
And why is it that?
No idea.
Okay, so let's at first examine this here. Let's say we have this carboxylic acid, and a base comes along, and it's going to steal the hydrogen from it, right? So I'm going to draw the conjugate base in red here. So this conjugate base now has a negative charge, correct? And it's lost hydrogen and it's gained the lone pair here. So what can happen is because we have this carbonyl here, it can resonate. If you remember from Chem 105, we can draw resonance structures. And then we can get this guy here. Right? And so it can resonate back and forth between the two. But really, it doesn't really exist like that. It's not like one has a double bond, one split second, and the other one has a double bond, another split second. So back and forth.
Maybe 1/2.
Yeah, they're really going like this. And so that means the negative charge has been delocalized. You hear that term a lot. Delocalization of the negative charge. That means this negative charge is really on both oxygens. So we can really think of it like there's a half negative charge on either oxygen. So let me draw this. We have acid plus base gives us a conjugate base plus a conjugate acid. And this conjugate base corresponds with that acid, right? And vice versa here. The weaker the conjugate base is, the stronger its acid was. And so that means a base, if we define our base, a base is either an electron donor or a proton acceptor, right? We can think of a base as either of those terms. So let me just draw, let's reference this to something else. So the pKa of this guy, what was the pKa of carboxylic acid?
4.7.
It's around 4.7. So what's the pKa of, blue markers sticking out up here, of say an alcohol?
About 15.
Yeah. Notice this is a lot more acidic than this. Yeah, this has a carbonyl. Carbonyl's electronegative, so it's pulling electrons away from the alcohol, from that hydrogen. But I mean, that probably is not going to make that big of a difference. So the reason why this is so much more, or so much less acidic than our carboxylic acid is the fact that when a base comes along and steals its hydrogen, this guy's conjugate base looks like this. And then can this negative charge delocalize anywhere?
It's stuck.
It's stuck there. Do molecules like to have negative charges on it? No, they want to be neutral. So first off, this alcohol doesn't want to give us hydrogen because it doesn't want to have a negative charge. It's unstable that way. The carboxylic acid, I mean, it doesn't really want to, but it doesn't mind because now it can stabilize this negative charge between two molecules.